let's look at a couple examples of using this cylindrical shell idea to calculate volumes. So let's start by finding the volume obtained by rotating the region under the graph of y equals e to the minus x squared, and between x equals 1 and x equals 2. And we're going to rotate about the y-axis. So going about the y-axis here, and we're going from x equals 1 to x equals 2. So that's this sort of wedge shape. It actually does have a flat right-hand side, but it's hard to tell because the right-hand side is so short. Okay, so that's like this. So x is going to be our independent variable. Right? One key thing about volumes using cylindrical shells is that your independent variable is perpendicular to your axis of rotation. If your independent variable is parallel to your axis of rotation, then you're going to end up with washers or disks. Okay, so we know that we're going to integrate from 1 to 2. We need the circumference of a circle, the circle traced out by the line segment at x. So, and the circumference is 2 pi times the radius times the height of the line segment at x, dx. So now all we need to do is figure out what is the radius as a function of x. The radius is the distance from the axis of rotation over to the position that we're at. Since our axis of rotation is the y-axis, the distance from the y-axis over to the x-coordinate x, that's just x. So r is just x in this case. And h, remember, h is the height of the line segment at this position, and the height is just, in this example, it's just given by this function. So that's e to the minus x squared dx. All right, now that we have this integral written down, we can temporarily forget about where it came from and just concentrate on figuring out what tricks from our bag of integral tricks will help us evaluate this integral. And it seems to me, because of the stuff up in this exponent, it seems to me like a u substitution is probably the right way to go. So let's let u be minus x squared. So du is minus 2x dx. Now we can rewrite this integral. So integral from, let's translate our bounds. So when when x is 1, we get u is minus 1 squared, so that's minus 1. So minus 1 is our bottom bound. When x is 2, then u is minus 4. So minus 4 is our top bound. It might seem at first a little strange that our bottom bound is actually a larger number than our top bound, but if that's what u substitution says, that's the way it is. Don't go switching them around just because you want the smaller number on bottom. Of course, now that we have them written this way, we could swap the bounds of integration, but if we also put a minus sign in front of this, but it doesn't hurt to leave it the way it is. So let's see. We have a pi. This 2, this x, and dx, those all go together to make minus du. Right? The second substitution equation here, if we multiply both sides by minus 1, it says that minus du is 2x dx. So here I've collected together 2 times x times dx. All of that together makes minus du. And then the last piece is this e to the minus x squared, and that's just e to the u. Okay, now this integral, so first of all, there aren't any x's left, so our u substitution is complete. And this integral looks easier than the one we started with, so our u integral is helpful. So we can keep this integral and evaluate it. So let's take the constant multiples out front. So we have a factor of minus 1 and a factor of pi. So let's move those out front. Minus pi times the integral from minus 1 to minus 4 of e to the u du. So this is minus pi, and then for an antiderivative of e to the u, how about e to the u? We're going from minus 1 to minus 4. So minus pi times, and then plug in our bounds, e to the minus 4 minus e to the minus 1. So this is, I guess, pi times e to the minus 1 by e to the minus e to the minus 4. We could dump this into a calculator to get some decimal approximation, but, this answer is just as good. All right, let's look at another example. Let's take the region enclosed by y equals square root of x and x equals 2y, and let's rotate it about the line x equals 5, and let's find that volume. I guess maybe the first thing to do is let's figure out what this volume is. So y equals square root of x looks something like this. X equals 2y. That's the same as y equals 1/2 x. So that looks like this. So there's the region that we're rotating. And we're rotating this about the line x equals 5, which is over here somewhere. So we're rotating it around here. The way that we have things written, things are sort of naturally expressed as functions of x. So why don't we use x for our independent variable? Also, I'm trying to do examples that involve using cylindrical shells instead of washers. So let's use x as our independent variable. That means we're going to get one vertical cross section for every x value, and these cross sections are going to swing around and make these cylindrical shells like this. Okay, so we're just going to integrate from whatever our bounds are. We're going to integrate 2 pi times the radius of a shell times the height of a shell dx. So we need to figure out, well, first of all, what are the bounds? The bounds are going to be given by these intersection points of the square root function and our line. So let's find those intersection points. So we have y equals square root of x and y equals 1/2 x. We can set those equals. So 1/2 x equals square root of x, and then just solve this for x. So square both sides, I guess. 1/4 x squared equals x. And then I guess multiply both sides by 4. X squared equals 4x. Move the 4x to the other side. X squared minus 4x equals 0. And then factor. X times x minus 4. And so we get x equals 0, which is an intersection point that we no doubt knew about already, but also x is 4. So this top intersection point is at x equals 4. So our bounds are going to be from 0 to 4. Okay, times 2 pi times the radius of a cross section. So the radius of the cross section, the radius of the cylindrical shell is the distance from the edge of the shell to the axis of rotation. So this red distance here. This is a horizontal distance, and to measure a horizontal distance, you take the large x-coordinate minus the small x-coordinate. The large x-coordinate is 5, and the small x-coordinate is x. So the radius is 5 minus x. Okay, now for the height. The height is this green distance here. And that's the distance between the square root function and the line. So all we need to do is take the larger y value minus the smaller y value, and that will give us the length of this green distance. Well, the larger y value is the square root function, so square root of x, and then the smaller y value is given by the line, and that's 1/2 x dx. So here's our integral. Since every term, when we multiply this all out, every term is going to have just a power of x in it, and so we can just use the power rule to integrate this once it's all multiplied out. So this seems like a pretty good strategy for evaluating this integral. I guess while we're at it, why don't we move 2 pi outside. So for this integral, we get 2 pi times the integral from 0 to 4. And now I'm going to multiply this whole mess out. So 5 times square root of x, 5 times minus 1/2 x, so minus 5 halves x, and then minus x times square root of x, so minus x to the 3 halves, and then plus 1/2 x squared dx. Okay, now we can integrate. So antiderivative of 5 times square root of x is, let's see, 5 times, we're going to have an x to the 3 halves, so we need a factor of 2/3 in here, minus 5 over 4x squared, right? So this, we need to sort of factor out a factor of 2 from the denominator, so that's why it turns into a 4. Remember, you can always check that this antiderivative is correct by taking its derivative and seeing if you get back to the term that we started with. Okay, now for this x to the 3 halves term, we're going to need 2/5 x to the 5 halves, and then plus 1/6 x cubed. And we're going to integrate from 0 to 4. All right, now we just need to plug everything in. Notice that for each of these terms, when we plug in the bottom bound, each of these terms will give us 0. So plugging in the bottom bound will just give us a 0. So we really just need the top bound here. So plugging in the top bound, we get, let's see, 5 times 2/3 is 10/3 times 4 to the 3 halves. We'll have to evaluate that later. Minus 5/4 times 4 squared. So I'll leave it as 4 squared because then we can just cancel like that. Minus 2/5 times 4 to the 5 halves plus 1/6 times, times 4 cubed. Okay, and now we have some arithmetic to do, but you know, the hard part is done. We've done all the calculus already. So 10/3, let's see, 4 to the 3 halves, 4 to the 1/2 is 2, and 2 cubed is 8. Minus 5 times 4 is 20, minus, let's see, 2/5 times 4 to the 1/2 is 2, 2 to the 5th is 32. Plus, and then 4 cubed is, let's see, 4 squared is 16, so cubed is 64. So 1/6 times 64. Okay, so 2 pi times, let's see, 80/3 minus 20 minus 64/5 plus, I guess we can simplify this, 32/3. Yes. Okay. And then, you know, to get an actual numerical result, we need to evaluate all this fraction arithmetic, but I think you get the idea. You can do the arithmetic for yourself if you like. So I think the important thing to keep in mind for this example is our axis of rotation was not a coordinate axis. So when we figured out the radius, we had to do this difference of x values instead of just being x, right? So if you look in a textbook at the formula for cylindrical shells, often they'll just have x instead of the radius. But using x for the radius only works if your axis of rotation is the y-axis. But in this case, it wasn't the y-axis, so we couldn't just use x. So really, it is better to keep in mind this geometric version of the idea for cylindrical shells, so that you don't actually, or so that you can handle this kind of situation where your axis of rotation is offset.